To understand the gradient descent algorithm, it is necessary for us to visualize the entire hypothesis space of a possible weight vectors along with their associated error that is shown in the diagram. So this is the hypothesis space. As I already told, an hypothesis space, it is nothing but the different hypothesis or the different predicted values of weight. So here we can see that this is a plane where we have W0 and a W1 vector, where the vertical axis, it indicates an error of the two vectors, that is an W0 and W1. So the arrowhead that is present here, it indicates the negation of an gradient descent. The negation of a gradient descent, it is nothing but, so this is a gradient descent, that is a peak value or the highest peak where the person is standing. So if the negation of it is done means, so it will become the steepest curve. So this is a negation of a gradient descent. So here the arrow mark that is present here in the diagram, it indicates the negation of a gradient descent. So here the axis that is a W0 and a W1, it represents the two weights. So as I explained earlier, so this two axis that is W0 and W1, it indicates the weight, and the vertical axis, it represents the error. The arrowhead that is present here means this part, this decreasing curve part, it indicates the negation of a gradient descent. The gradient descent, as we all know, the gradient descent search, it determines the weight vector that minimizes the error by starting with an arbitrary initial weight vector, and then repeatedly we are going to modify it with a certain or small steps. So that is the rule of a gradient descent applied to a delta rule. So what is a delta rule applied with a gradient descent is that randomly we are going to choose any weight vector, and then we are try to minimize the error. This is a continuous process until we get the best weight. So at each and every step, the weight vector, we are going to alter it in a direction that it produces a steepest descent. So every time we are going to alter the weight so that we get the steepest descent or the decrease in an error. That is, you can observe here. Now this process is repeated until we get the global minimum error. So what is a global minimum error is this point. So this point where we have the least error and we get the best weight. So that is a global minimum point. At this global minimum, we tell that the error is completely reduced, or we say that when the error is completely reduced, the predicted value is near to a target concept, or the predicted value, it is equal to an exact value when the error is decreased or when the error is 0. So visualizing the hypothesis space, so I'll just revise it again. So here we need to understand what an hypothesis space is. Hypothesis space, as I earlier told, hypothesis space, it is a collection of many such hypotheses or the collection of many predicted values. So this is our hypothesis space where we have an axis of an W0 and a W1 weights we have considered. Many such different weight vectors also we can consider to determine the weight. The vertical axis here, it represents an error, whereas this arrowhead, it defines or represents the negation of an gradient descent, that is a decrease in a error value. So that is the negation of a gradient descent. It is indicated by this arrow mark. So as we all know, a gradient descent method, here we are randomly going to choose a weight vector and we try to minimize the error by starting with an arbitrary value, and then repeatedly we are trying to modify the weight step by step so that there is a decrease in this error, and then we are going to get a steepest descent. So this steepest descent where we have the least error or the minimum error that is called as a global minimum point, where we have a minimum error, where we have an exact weight, and we say that the predicted value is equal to an target function. So this is an hypothesis space of a 3D diagram. This is also an hypothesis space of a 3D diagram. Here you can observe that it is a local minima, these are the saddle points, and this is a global minimum point. Now if I draw a diagram and I'll show what is an So I'll draw a curve like this. So this is called, this peak point, it is called as a local maxima. This least point, it is called as a local minima, and whereas this point is a saddle point. And if I draw a still more point like this, and this is going to be my global minimum. So what is this? This is my local maxima, where it is highest of compared to all the peaks, whereas this is local minimum, and this is a saddle point. The saddle point, it is a min max point. And next this the steepest of all, it is called as a global minimum point, where we have the least error. The same diagram what I have written here, local maximum, local minimum, saddle point, next we have a global minimum. The same thing it is shown in this diagram in a 3D representation. Same thing in a 3D representation it is shown. Now let's take an example of visualization of an hypothesis space with an example. So here the diagram what I have considered here, the two parameters I have considered. The one parameter, it is a weight, and the next parameter, it is an height. So now it is a data set. So these points are the data set that indicates the height and the weight. The x-axis part, or the first point, that is a 0.5 comma 1.4, where 0.5 indicates the weight and 1.4 it indicates the height. Now here we have to find out the error, or we can say that the residual. In a simple meaning, an error is nothing but an residual, which is a difference between the actual value and the predicted value, or else I can say that an error, it is a difference between actual value minus predicted value. Now this is a linear line that is drawn here. It is not classifying an height and weight accurately. Now so we are going to minimize the error for this. So how to minimize the error? Let's learn it by using this example. So we are going to apply an gradient descent method. Gradient descent method, here it is applied since we have to minimize the error. So by minimizing the error, we can get a best fit line with an optimum values, so that we can properly classify this data points, or nothing but the data sets accurately based on their height and weight. Now what is the formula we are going to use for that is predicted height. So here we are going to predict the parameter, that is an height parameter we have chosen. The predicted height, it is equals to intercept plus slope into weight. So this is a formula we have chosen since it is a linear line. So since it is a linear line, this we have chosen. So now what is an intercept? So intercept, it is a point where the linear line cuts the x-axis or the y-axis. If it cuts the y-axis, then it is called as an y-intercept, and if it cuts the x-axis, then it is called as an x-intercept. Now we are going to predict an height for each of the sample, that is, so we are going to predict the height for each of the sample, or the data example, or the training example what we have chosen here one by one. So the predicted height, it is equals to intercept plus slope into weight. The formula is considered here. The intercept, since it is not cutting any of the axis, so here we can observe that it is not cutting any of the axis, it is starting from the origin. So that's why the intercept we have chosen here, it is equal to 0. So 0 plus slope, it is a 0.64, it is assumed value, or in the, if this problem is given, it will be given in the question paper, or you can just assume this the same value and continue the problem if it is a theory question. So 0.64 into weight. So what is the weight that is given here for the first sample? It is 0.5. So that 0.5 it is taken here. So understand here it is 0.5 comma 1.4, where 0.5 here it indicates the weight, that is an x-axis, and 1.4 it indicates the height, that is an y-axis. The same way here 2.3 it indicates the weight and 1.9 it indicates the height. 2.9 indicates the weight and 3.2 it indicates the height. Now, so this is a calculation part. So we are going to get 1.42. So we have to find the error here. So I told error or the residual both are same. It is nothing but an observed height or the actual height minus the predicted height. So actual height we have got here is 1.4 minus predicted height we got is 0.32. So if we take the difference, it is going to be 1.1 is the error. Now the same thing it has to be done for the second sample. For the second sample, the weight considered here is 2.3. So 2.3 is the weight we have considered. So if we do the calculation, we'll get the predicted height for second sample is 1.42. Next, residual for that is observed height. So observed height here is 1.9. So 1.9 minus 1.42, we are going to get 0.4. Same thing for the third sample if I do. So we are going to get the residual as 1.3. So now we have to square sum of the squared residuals so that we get the total error. So if I do that, it is going to be 3.1. Now since the intercept was 0, I told what is an intercept? It is a line that cuts the x or y axis. Here I have assumed the line to be starting from an origin. Now if I draw a line from here, if I draw a line from here, then I'll say that it is cutting the y-axis. This point is cutting the y-axis, and this value it is said to be an y-intercept. Now, if I choose an intercept value to be 0.25 and continue the calculation in the same manner, that is for the first sample, we know that the predicted height formula is intercept plus slope into weight. So intercept I have chosen here to be as 0.25 since it is cutting the line. The linear line is cutting my y-axis at 0.25. So 0.25 plus 0.64 into weight. So how we got 0.5? It is from the diagram, that is weight comma height. So I have written here 0.5. Next, again the same way the residual is calculated. So residual, it is nothing but an error, that is an observed height minus predicted height. So I am going to get 0.83. Same thing repeated for the second sample and for the third sample. And finally I am going to do the sum of square of the residuals. So all the residuals from the equation 1, 2 and 3, I am going to square it and I am going to add it. So if I compare the first star value was 3.1 and the second star value is 1.9. So what is the change here is in an intercept. So in a previously assumed the intercept of a line was 0 since the line was starting from the origin. Now since I have drawn a line that is drawn in a pencil, it is starting from some intercept value that is 0.25 if I assume, then the second star equation that is giving the sum of the residuals, it is 1.9. So from these two star equations we can observe that as and when the intercept value is increased, as and when the intercept value we are increasing, we are going to reduce the error and we are going to get the parabolic graph. So this is a parabolic graph. So as and when the intercept we are going to increase, then we are going to get the less error. This is a plot of sum of square versus this is an intercept. So this diagram, it is of an x-axis indicates an intercept and the y-axis indicates a sum of squares. So as and when the intercept is keep on increasing, so I am going to get the sum of square at a decreased point. So this point is decreased and this is called as a global minimum point. So this is my global minimum point and where I have the least error. So this is a least error. When I have the least error, I am going to get my best weight value. Best weight value, I am going to get it. And when I have a best weight value, my output will be accurate, means my predicted value will be equal to my target value or my exact value. So this is a method of an gradient descent visualization. Gradient descent visualization. Now if this is a formula of a sum of squared residuals. So it is a residual minus, so whatever the steps I have done here, completely the same thing, if I put it in terms of a formula. So how I have got a sum of residuals, sum of squared residuals, how I have got it is 1.1 square. So what is 1.1 square? So 1.1 square I have got from 1.1 I have got from residual equation 1. Next, how I have got plus 0.4 square, it is from the equation 2. So it is a square of the residuals. So how I have got the residual? It is an observed height minus predicted height. The same thing if I put everything in a formula. So sum of a squared residual, it is nothing but a residual minus an intercept plus slope into weight, the whole square. How many times I have to repeat this? This depends on the samples. Here I have considered only 3 samples. So here we can see that I have considered only 3 samples. So that's why so this formula, it should be repeated 3 times, or else you can do it directly, or you can do in terms of steps like this. So first we have to calculate the predicted height of each and every sample. Correspondingly, you have to calculate the residual of each and every sample. Next, we have to perform the sum of the squared residuals, or directly if I write a formula, it is residual minus the intercept plus slope into weight, the whole square. How many times? It depends upon the number of the data samples or the training examples we have chosen. So quickly if I revise it off. So if I revise this again, so visualization of a hypothesis space. So we are going to visualize an hypothesis space, where we have many predicted values. So this is an hypothesis space where we have an W0 and W1 weight vectors. Different weight vectors we can choose it, whereas the y-axis or the vertical axis, it represents an error of a vector, weight vector. So this arrow mark, it indicates the negation of a gradient descent. So negation of a highest peak, if I do it, then it's obvious that I am going to get the parabola. Negation or the knot of an highest peak, if I do it, so I am going to get the parabola like this. So we know that in a gradient descent method, we are going to choose the weight randomly. Then we are going to find out the error. We are going to apply the steepest descent method. So we are going to decrease the error for each and every assumed weight. The weight will be updated continuously and error is calculated at each and every step, so that we get the best output. So what is meant by best output is, it is nothing but the predicted value, it is matching with an actual value, then it is called as a best fit. So how to get a best fit is when we get a minimized error. So this point, it is known as a minimized error, or it is called as a global minimum error. So when we get a global minimum error, so error is 0 or error is least, we are going to get the best weight. When we get the best weight, we are going to get the best output or the best target function. This is well explained by considering this example. Here we have considered the two parameters, that is an height and a weight example. So for 3 samples I have considered. So now since it is a linear line that is drawn, it is not perfectly classifying the height and weight of a person. So what is the formula to calculate the predicted height is, it is an intercept plus slope into weight. So slope I have assumed here as 0.64 and intercept, since for the first example the intercept is starting at 0 and for the second linear line which is drawn randomly, for the second line it is 0.5. The same way you can take here also the line and say that the intercept value is 0.5. So or you can say that it is 0.4. Any intercept value we can take it depending upon the linear line we are drawing here. So here I have drawn a line and I have taken some random value as 0.25, just to show that as and when the intercept values keep on increasing, the error is keep on reducing and we are going to get a perfect parabola. When we get a perfect parabola, we are going to get a global minimum. So predicted height, it is equals to intercept plus slope into weight. So we are going to do the calculation by assuming intercept equal to 0 and slope equal to 0.64, and we calculate an residual for each and every sample like this, and finally found out the sum of the squared residuals. If the intercept value is 0.25, again we did a calculation. We compared the two star values, that is the first value when the intercept was 0 is 3.1 and when the intercept is 0.25 the value is 1.9. So since 1.9 is less when compared to 3.1, we say that as and when the intercept value is increasing, we are going to get a perfect parabolic graph. When we get a perfect parabolic graph, we get a reduced error. So this is a parabolic graph where we have an intercept on the x-axis and sum of squared residuals on the y-axis. So when we get a global minimum, we get the best weight. When we get the best weight, we get the best output, that is a predicted value is equal to an actual value. So if we want to do the calculation directly, that is the sum of squared residuals, this is the formula. Now what is the minimum and what is the global minimum, local maximum? Is the highest point is local maximum, the lowest point here it is local minimum. Minimum, maximum, min, max, it is a saddle point, and the least of all the peaks here it is the global minimum. This is about visualization of gradient descent.